Hello, welcome to the Mastering ARM Assembly Language course. In this course, you will learn the fundamentals of the assembly language and explore the ARM architecture and its instruction set. Assembly languages are the low-level programming languages specific to the particular computer architectures. Here are some of the major types of the assembly languages. But in this course, we will be particularly focusing on the ARM assembly language. By understanding ARM assembly, programmers can work at the low level and write code that works with the hardware more efficiently. By end of this course, you will gain the fundamental understanding of the ARM processors. You will be able to write assembly programs with various instructions. In this video, let's discuss about ARM assembly. Assembly language is a low-level programming language that is closely related to computers' machine code instructions. Unlike high-level languages like C, assembly language provides more direct interface to hardware. When you write low-level code, you are closer to hardware and you write better interaction between hardware and software, allowing programmers to write instructions that are executed directly by CPU. Now let's understand assembly by taking an example. The following example is an example of addition instruction. Let's break down this instruction. Add is an operation, while x1 is a destination register, whereas x0 is a source register, and #1 is the immediate value. This instruction adds the value 1 to the contents of the register x0 and this stores the result in the register x1. Now let's discuss more about ARM. ARM architecture is family of RISC. ARM processors are extensively used in consumer electronic devices, for example smartphones, tablets, and other electronic devices. Because of their reduced instruction set, they require fewer transistors. In simple words, they require lower power consumption. Due to this, they are most suitable for IoT devices. At end, let's discuss about ARM thumb mode. When ARM thumb mode is active, 16-bit instructions are executed instead of standard 32-bit instructions that are used in ARM mode. It is an execution mode in ARM processors designed to enhance density and improve performance in memory constrained environments. It achieves it by using a subset of ARM instruction set. In this video, let's talk more about registers in ARM. A register is a small but fast storage location within a computer CPU. Registers are used to quickly store and retrieve data that CPU needs to execute. They are essential components of a CPU, enabling it to perform calculations, manipulate data, and manage execution flow efficiently. ARM architecture features a set of general purpose registers. There are 30 general purpose registers in 32-bit architecture that are used for arithmetic, logical operation, and data movement. The number and naming of these registers slightly vary between 32-bit and 64-bit ARM architectures. The first 16 registers are accessible in user level mode. These 16 registers can be split into two groups: general purpose registers and special purpose registers. Now let's see 32-bit ARM registers and how they relate to Intel 32-bit architecture. The first register in ARM architecture is R0, that is a general purpose register, and you can relate it to EAX in Intel. While R1 to R5 are also general purpose registers, but you can relate them to EBX, ECX, EDX, ESI, and EDI in Intel. R6 and R10 are also general purpose registers, while R11 is a frame pointer, and R12 is used for intra-procedural calls. R13 is a stack pointer. Stack pointer points to the top of the current stack and is used for the function calls, local variable storage, and context switching. You can also relate it to ESP in Intel. R14 is a link register. It stores the return address for the subroutine calls and facilitates nested function calls and returns. R15 is a program counter or instruction pointer. You can relate it to EIP in Intel. The program counter holds the address of the next instruction that is to be executed. It automatically updates when each instruction is fetched. CPSR or current program state register. You can also relate it to E flags in Intel that indicate the current state of the processor. Example 0, negative, carry and overflow. It controls processor modes and interrupt setting. Now let's further discuss CPSR. The following table shows the flags that are available in the CPSR or current program status register. The first flag is a negative flag. It is set when the result contains the value that is negative. Zero flag. It is enabled when the result or the value is 0. Carry flag. It is set when the value requires 33 bit to be fully represented. Overflow flag. It is set when the value cannot be represented in 32 bits 2's complement. The next flag is a Jizzle flag. The third execution state that allows some R processors to execute Java bytecode in hardware. The next flag is Indianness flag. It is set 1 when the ARM processor works at Big Endian mode and set 0 when it works at Little Endian mode. The ARM can operate either in Little Endian or Big Endian. The next flag is thumb bit flag. This bit is set if you are in thumb state and is disabled when you are in ARM state. In the next video, we will talk about Indianness. In this video, we will talk more about Indianness. Little Endian or Big Endian. The major difference is the byte order, in which each byte of the object is stored in memory. On Little Endian machines like Intel 32-bit or 64-bit, the least significant byte is stored at the lowest address. The lowest address is the address closest to the 0. On Big Endian machines, the most significant bit is stored at the lowest address. Now let's simplify it further. Here we are having an example of 32-bit. In 32-bit, there are 32 bits and total 4 bytes, as 1 byte is made up of 8 bits. So here we have byte 0, byte 1 and byte 2 and byte 3. Each byte contains 8 bits of memory. Each bit can either contain 1 or 0. So least significant byte here is byte 0 and most significant byte here is byte 3. In Big Endian, we have byte 3 or most significant byte at lower address. As you can see, the direction of address is in increasing order. We are moving from lower address to the higher address. In Little Endian, we are having byte 0 or the least significant byte at lower address. Or in simple manner, in this stack at being Indian, first byte 3 is stored, then byte 2 is pushed, then byte 1 is pushed, and then byte 0 is pushed. While in Little Indian, first byte 0, then byte 1, then byte 2, and then byte 3. So in Little Indian, byte 3 is at the higher address. So whenever the stack pops up, the byte 3 is gonna pop, then byte 2, then byte 3, and then byte 0. In this part of the course, we are going to talk about ARM instructions. The purpose of this part is to briefly introduce about ARM instructions. As mentioned earlier, assembly language is composed of instructions, which are the main building blocks. ARM instructions are usually followed by one or two operands as the given syntax. First the mnemonic and then the optional suffix, and then you require a condition that is needed to be met in order to instruction to be executed. The condition and the optional suffix are not necessary to include. And next we are having the destination register that is used for restoring the result. Then we have operand 1 and operand 2. These operands can either be a register or the immediate values. Now let's have a look at the instructions and their descriptions. These instructions can be categorized into 5 types: data processing instructions, load and store instructions, branch instructions, control instructions, and shift instructions. As you can look all the instructions and their description in this table. In further lectures, we'll have a further and deep look at each of these instructions. Now let's talk about move instruction. The move instruction in ARM assembly is used to transfer data from one register to another, or you can load an immediate value into a register. It is one of the most basic and frequently used instructions in ARM assembly or any assembly language programming. As you can see, the syntax for the move instruction is that first we are using move instruction and then the destination and the source. And example is as follows, where you are loading an immediate value 5 into a register R0. For the practical side of this course, we will be using Simulator. It is a full system simulator for ARM v7 that runs in web browser. Now let's jump and start some move instructions. First let's try with moving an immediate value into register. Now here, what we are doing is that we're moving an immediate value 1. It is decimal value that we are moving into R0. Now let's try and compile it. Now if you see, as I step into this instruction, the decimal value 1 is added into R0. Now let's try and move a value of register into another register. Now here, the value 1 has been stored into R0, and in the next instruction we are moving that value 1 from register R0 to R1. Or you can see in the next instruction we are just moving the value of R0 into R1. If we change the value decimal from the hexadecimal, or we can take another value this time. Let's take Now as you see, after the first instruction, the value 2 has been changed into register R0, and after the next instruction finishes, the value of R0 has been changed into R1. Now let's check out the add instruction. The add instruction performs the addition operation between the two operands and will store the result into destination register. The syntax is a little same as the move instruction. First you have the add mimic, and then you have the destination register followed by your operands or the source registers. You can also add immediate values and then store into a destination register, or in simple words, the operands can be immediate values as well. For example, here we are storing addition of R1 and R2 into register R0. Here the addition of immediate values of the R1 and R2 will be stored into R0. Now let's see add instruction little practically. I have already written the code for the add instruction. In the first line of the code, we have move instruction where we are loading the immediate value 5 into register R0, and in the next line we are having another move instruction. We are moving the immediate value 10 into register R1. Now as we previously discussed, add instruction add the numbers or the values from the sources and stores into destination register. Here the destination register is R2 and sources are R0 and R1. Now let's check what happens at the back of the hood. After the first instruction, the value 5 is added into register R0, and as you know, in the hexadecimal, A represents the decimal value 10, and the third instruction will add the R1 and R0 and will store into R2. The addition will be 15. As if we convert the hexadecimal format into decimal format, you can see R2 contains the value 15. Now let's talk about the sub instruction. Sub or subtract. This instruction is used to perform subtraction between two operands. Here we are having a syntax of the sub instruction where first we are writing a sub mimic, then we are writing the destination register, then we are writing a source one or the source register. Here the source one should always be a register. You cannot take a immediate value as in the place of the source one, and source 2 can be a register as well as a immediate value. So let's take an example. In example, we are storing the result of R1 and R2 where R1 is a greater number and R2 is subtracted from R1 and is stored into R0. There is no necessity of R0 being a greater number, as ARM instruction set can also contain negative values as well. Before getting further, let's change the format from hexadecimal to decimal and see how the values in register changes. After the first instruction executes, the R2 holds the value 3, while After the second instruction, the R1 will hold the value of 7. When the sub instruction executes, value of R1 was greater than value of R2, and R0 will be containing the result of R1 minus R2, which should be 4. As you can see, R0 now contains the value 4. As R1 contained the value 7, which was lesser than the immediate value 10. Now R0 would be containing a negative value. Now we have the mul instruction or the multiply instruction. This instruction is an arithmetic instruction that is used to multiply two operands, and the result is stored in the destination register. It is very similar to the add and subtract instruction, where you are having two sources and one destination. In this example, we have taken the destination register R0 while the sources are R1 and R2. Here you can take both the sources as the immediate values. In example, we are storing the result of the R1 and R2 when multiplied in R0. Now let's see what really happens to the registers. Before we proceed, let's make the format decimal. Now, in the fourth line of the code, we are having the move instruction, similar in the fifth. In these instructions, we are moving the immediate values into the register 1 and 2. These both values are positive, and when multiplied will contain the result 12 that will be stored in the 0. That's a very simple one. Now let's move to the line number 7. Here we are having a move instruction, and the value that is moved in the register R1 is an hexadecimal value. In hexadecimal, this value means -3 in the decimal. As you know, -3 when multiplied with plus positive 4 will have the value -12 that will be stored in register R2 in the line number 9. So now, before any further ado, let's compile and load. As you can see here in the line number 7, our move instruction that was to move a negative number to the register R1 has been changed. This MVN instruction is move the note instruction. This instruction moves the note of the immediate value into a register, or note of the value contained in register to the destination register. Here, this has made the note of 2 value into the R1, which will be 3 or minus 3. So let's step into the instructions. After the first instruction, our R1 has gotten the value 3 and R2 has become 4. After the multiplication, R0 will be 12. After the 7th instruction or the 7th line instruction, our R1 will be -3, as you can see, and R2 will be as before 4. And in the last instruction, our R0 will be -12. Now let's start with the load and store instruction. These both instructions are the foundational instructions for moving the data between register and the main memory. Unlike Intel architecture, in ARM architecture, Only these two instructions are capable for moving the data between register and the main memory. The LDR or the load instruction, this loads the value from the memory into a register, while in the store instruction, this store the value from a register into a memory. As you can see in the syntax of the LDR, first you require a destination and the address from which you are loading a memory or the value, while in the store instruction you require a source and then address. Source is the location from where you are getting the value and the address where you are moving the value. Now let's check load and store instruction in CPULater. ARM uses load and store architecture. That means only load and store instructions are allowed to access memory. Unlike Intel architecture, where complex instructions can also access the memory and change them. Now let's start with the video. First I'm gonna add a data section where you can store data that you cannot store directly into a register. As you can see, the data section have changed the color like a keyboard. Now let's declare a variable that will be a word variable with an immediate value. Let's give the variable immediate value 3. Let's be a creative here and name the variable. Here I have declared a variable with a value 3. Now let's declare another variable. Let's give this variable value 5. Now let's start with the load instruction. Now you would be thinking, why cannot we be using the move instruction to move the value or an address of the variable into a register? You simply cannot use that. And if you did so, your compiler will throw an exception that this is not permitted. Now in this instruction, you would be thinking, why did I add this equal to sign? The LDR instruction with an equal to sign is used to store the load address or is used to load the address of a variable into a register. Now this instruction without equal to sign loads the value at the memory address labeled variable or labeled VAR. Now I really did a mistake at naming. Let's name it VAR1. If you're not having equal to sign, it will try to store the value at VAR into R0. To access the address of VAR, we need to add equal to sign. Now let's compile and check that into the register. Now let's step into the instruction. As you can see, 8 has been added to R0. Now you would be thinking the value was 3 and it's not even closer to 3 or doesn't seem like an address. If you are working with an Intel or you are doing directly into your PC, this is not kind of address you will get into your register. Now let's look at the memory. If you see, 3 has been stored here and we even declared another variable that was 5 and 5 seems to be here. As you know, in 32-bit architecture, this is a address 0, and similarly this is address 4 by the difference of the 4 bytes, and this would be address 8 and this would be address 12. What if you need to directly store the value of that variable? As we have already stored the address of the variable into R0, it would be now pretty easy to do that. Now let's store the value of variable 1 into R1. Now this instruction loads the value from the memory address stored in register R0 into register R1. Now these square brackets are pretty much like dereferencing the pointer in C. Instead, here the value of R0, or the value that was stored in the address of R0, will be stored into R1. Now let's compile and check it into memory. As you can see, now R1 contains value 3. Now you would be thinking, previously it was having the value 8. Now it has been switched to value 10. Why this so? As you can see, now our value 3 has been moved to address 10. Moving of the values is pretty much common. You don't need to worry about that. Now let's check out the store instruction. As I have previously mentioned in the previous part of the video, that store instruction is quite the opposite of the LDR instruction, where in the LDR you are storing the address or value from the address into a register. It's kind of moving from memory to register, while in the store instruction you are kind of moving from the register to memory, where you can store the value from the register or the address from the register into your memory. So we have already written some code where we have stored the value from the variable 1 into register R1. Now let's use the value from the variable 1 and that has been stored into register 1 to move the value from register 1 into variable 2 that has been holding the value 5. So first let's load the address of the variable 2. Now let's load that address into register 0 because we don't need that anymore. For the store instruction, we are using the str mimic, and the source will be our R1 and the destination is gonna be R0, as R0 is containing the address of variable 2. We are gonna use that square braces again and R0. Now let's check out how it performs in the memory after when you compile it. As you can check in the memory, the place they are holding is 4, 5, 34, 4, 8, 12, 16, 20, 24 and 28. The value 5 has been held at the address 28. So the R0 should be 28 after when you step over. As you can see, 1 is a 28 in the decimal, and after the store instruction, this value 5 should be changed into value 3 from the register R1. As you can see, the value that has been stored here was 5, now has been changed into value 3 from the register R1. So this is how you can move the data from memory to register and register to memory. In this video, let's talk about LDM and STM, which are the instructions for loading multiple and storing multiple values. In our previous video, we discussed about how we move data between a single register and a single memory address. Let's start with LDM instruction. LDM instruction is used to load multiple registers from a consecutive memory locations. This instruction is highly efficient for handling operations where multiple registers need to be loaded from memory, such as storing a register state from a stack or loading a block of data. Here you have the syntax for the LDM instruction. Here the condition and exclamatory sign operator are really optional. You don't require them. Even if you are using a exclamatory sign operator, this indicates that the base register, that is Rn, should be updated after the operation. In the register list, you will put the values or the number of registers that are required, where you are going to move the values from the memory locations. There are major 4 addressing modes in both LDM instruction and STM instruction. Those modes are increment after, increment before, and decrement after and decrement before. As you can see, this whole mimic means load multiple increment after. This is similar with the other 4 load mimics and other 4 store multiple mimics. Now let's start with the store multiple instruction. The store multiple instruction in ARM assembly is used to store the contents of the multiple registers into consecutive memory locations. This instruction is useful for saving the state of registers to the stack or any other contiguous memory block. Now you will be thinking, what is the use of these two instructions? For saving the state of registers into stack, especially when before entering a function. For example, when entering a function, you may want to save the current state of the registers so they can be restored upon return, and load multiple can be used to restore those registers. Now let's understand this mode at CPU later. Now let's discuss load multiple in CPU later. Let's take the base register R0. As I discussed, there were 4 addressing modes: increment after, increment before, decrement after, and decrement before. If you by default use LDM instruction without addressing or specifying the address modes like IA, the default addressing mode will be IA. That won't matter if you specify IA or you simply write the mimic LDM. Let's take the base register R0. For the registers in which the values from the memory addresses will be moved. Let's use the registers R1, R2 and R3. For this showcase how this really works, the LDM instruction loads the value address of R0. Here, if you check in the registers tab, you will see the R0 contains the memory address, which is all zeros. If you go to the memory section and if you check the address where all values are 0, you will find this. And the R1 will be taking the value of R0 address, and R2 will be taking the value from R0 plus 4. As you can see, at plus 4 we are having the value where all the bits are A's, and the R3 will be taking a value of R0 plus 8. This is the incrementation of all 4 bytes. If you are having a R4, that will be incremented 4 again. That will be R0 plus 12. Now let's change the values in the memory section. That will make it easier to observe the process of LDM. Let's first make this decimal sign and making the values, let's put them random. 3, 34 and 5 and 0. As you can see, now according to the LDM instruction, R1 will be containing the value of 0, R2 with the value 3 and R3 with the value 5. Let's compile and run. After this step into, as you can see, the memory here has been changed, as it should be 0 here as we changed, but whenever a process is started, by default addresses are changed, as we have already seen that before once. So at the address 00, where all bits are zeros, this value has been moved into R1, and as after the 4 bits we have the value 0, which is moved into R2. Similarly with the R3. Now let's look for the store instruction. As store instruction moves the values from registers to the memory, let's load some values into registers first. Before doing that, let's refresh the emulator. As we are going to use the registers R1, R2 and R3, let's move the values into R1, R2 and R3. As now R1 contains the value 3, R2 with the value 4 and R3 with the value 5. Now let's write an store multiple instruction. There is no necessity of writing the store multiple instruction in the capital case, but for my personal satisfaction, I am writing those in the capitals. Let's take the source register R0. where the address from R0 will be taken as the base address. Now what really happens here is the address of R0 now contains the zeros, all zeros, and the value from R1 will be moved at address of R0, and value from R2 will be moving at address of R0 plus 4, and R3 will move the value from R3 from to the address R0 plus 8. As you can see, this will now be containing the value 3, and this with 4, and this with 5. Now let's compile and run. As you can see, by default these are the values that has been given to these memory addresses on the start, and after you step into the instructions, after you move the values into a register, and now before stepping in to these store multiple instructions, these are the values at the given addresses. Now if you step into, this is how the values has been changed, and the value from R1 is at this address, which is the address of R0, and this is address of R0 plus 4, which is containing the value from R2, and this was the address of R0 plus 8, which is containing the value of R3. And this is all for this session. In this video, we will be discussing about the logical operations. Logical operations in ARM assembly involve the manipulating bits within the registers. These operations are crucial for the tasks like bit masking, setting and clearing specific bits, and performing logical operations. Now, there are the 5 operations that store the result into a destination register, while these 2 logical operations do not store the result into a destination register. Else, they update the CPSR flags, which are the current state program status register. The AND operation performs the bitwise AND between the 2 operands. The OR operation performs a bitwise OR between the 2 operands. EOR performs a bitwise exclusive OR between 2 operands. BIC clears the specific bits in a first operand that we set in the second operand. MVN inverts all bits of the operand, which is similar to the NOT operation performed on the operand. The TST and TEQ in ARM assembly are used to perform bitwise comparisons between registers without storing a result. These store the result into CPSR. As I discussed, these flags can be used for the conditional branching and other conditional instructions. The TST performs the bitwise AND between the 2 operands, and the TEQ instruction performs the bitwise exclusive OR between 2 operands. Now let's see this more in the CPU later. Here I have already written the code that we will be discussing in this video. Here in the first 2 instructions, I have loaded the value into a R1 and R2, where in the instructions from line 6 to 12, I have written all the other logical instructions. The values that I have already loaded are similar to this binary code. If you substitute 1 with F, you will be getting the similar code. Now in the AND operation, if you pass the 0 at the both values of A and B, you will be getting 0. Similar to if you pass 1 and another with a 0 value, you will be still getting 0. This is the truth table of AND, and this is the truth table of NAND, which is the NOT of the AND operation. And the NOT operation This will reverse your inputs. In the OR operations, which will give you the 0 as a result if you are passing both the values 0 and 1 if either of the values is 1. But in the XOR operation, if the both of the values are same, the result will be 0. If both of the values are different, we'll be getting the 1 as a result. Here, if you see in the AND operation, the both of the values are different. In this case, you will be getting 0 as a result. In the NAND operation, you will be getting 1, which will be all F's. And in the NOT operation of any singular register, this will make the value to be turned. If you are passing this into a NAND operation, you will be getting this as a result. Well, if you pass this as the input into a NOT operation, you will be getting this as a result. In the OR operation, all this both inputs will give you the result as all ones. In the XOR operation, this will be giving the same result of the OR operation. Now let's compile and run. After loading the values into register R1 and R2, let's make these hexadecimal, and after the AND operation, you should be getting all zeros into R3, and after the OR operation between R1 and R2, you will be getting all F's into the R4. Similar that was we discussed with the XOR operation. And in the BIC, what really happens is you will perform NOT operation on the R2 register, and that will the result, let's store that into R4, and the BIC will make the AND operation of R4 and R1. So this is how the BIC looks like. So if you perform NOT operation on R2, you will be getting R1, and if you perform AND operation between R4 and R1, you will be getting this same as R1. And if you step into R6, we should be containing the same value as R1. As you can see, the R6 contains the value of R1. And if you perform the NOT operation over the R1, you should be getting the value of R2. As you can see, this contains the value of R2. For the TST and TEQ instruction, let's first make this decimal signed. As you know, TST was the AND operation, and if you see the AND operation between R1 and R2, which was the 6th instruction, and the result was stored into R3, and it contains the value 0, which should be setting the 0 flag. And for the TEQ instruction, that was XOR operation, and the result was stored into R5. As you can see, the value is -1, and this should be setting the negative flag. So TST should be containing the 0 flag, and for the TEQ instruction, it should be containing a negative flag. Now if we jump over to the CPSR register and making it again hexadecimal, now you can see the CPSR flag and the corresponding flags. After the TST instruction, the 0 flag has been set, while after the TEQ instruction, negative flag has been set. So this was all about the logical operations. In this video, let's look at the shift and rotate operations. These operations are fundamental techniques that are used in digital computing for manipulating binary data at the bit level. The first instruction we are having is LSL, that is logical shift left. The LSL instruction shifts the all bits in a register to the left by a specified number of positions. Here, in the syntax of the LSL, we are talking about the shift amount as the specified number of positions. As we can see in the diagram, from the least significant bit LSB to the MSB, the bits are shifted towards the left, and the empty space that is created by LSB is filled with zeros. The syntax for the LSL is LSL mimic, that is followed by a destination register, that is followed by a source register, and followed by a shift amount. The next instruction, LSR, is quite opposite to the LSL. The LSR, or the logical shift right instruction, shifts the bits of the register to the right by the specified number of positions. The zeros are shifted into the most significant bit to the leftmost bits, and the bits shifted out of the least significant bit are filled with the zeros. As you can see, the bits from the MSB to the LSB are shifted towards the right, and the empty space that is created at the MSB is filled with the zeros. The logical left shift, or logical shift left, is the multiplication of 2 with the source, while the logical right shift is the division of the source with the 2. And if you are shifting a byte with a shift amount 1, you are simply multiplying it with the 2. While if you are shifting it with the shift amount 2, you are multiplying it with the 2 to the raised to power 2, which is 4. Now let's look at the arithmetic shift right. The arithmetic shift right is little bit similar to the LSR, that was the logical shift right. The ASR instruction shifts the bits to the right by the specified number of positions. The most significant bit is replicated to fill the leftmost bits. This operation is used for the sign numbers and maintains the sign of the original value. So what do you understand by this? As you know, the negative of any value in ARM assembly is its 2 complement, and if you get a 2 complement of a positive number, the most significant bits will be 1, and the most significant bit of the positive number will be 0. To maintain the sign of the original value, the most significant bit is not replaced. As you know, after the shifting of the bits, the most significant bit is copied to the most significant bit of the result. Now let's take a look at the rotate right and rotate right with extent. The rotate right instruction in ARM assembly rotates the bits of the register to right by a specified number of positions. Unlike a logical or arithmetic shift, the bits that are shifted out on the right are wrapped around and reinserted on the left. As you can see in this example, we are having a byte where the LSB is 0 and the MSB is 1. After the rotate right operation, this LSB moves from the 0 from the LSB moves to the MSB in the rotate right with the extent. The instruction in ARM assembly rotates the bits of a register to the right by one position using the current state of carry flag as the new most significant bit. This operation effectively allows for the rotation that incorporates the carry flag, making it useful for certain algorithms and bit manipulations. Now let's wrap up this session. In logical shift that corresponds to multiplication and division by 2, the arithmetic shift is something that is related to the 2's complement representation. The rotate has no ordinary mathematical meaning and is almost an absolute operation even in the computers. Now let's take a look at conditional execution and branching. We use conditions for controlling the program's flow during its runtime, usually by making jumps or executing some instruction only when condition is met. The condition is described as a state of a specific bit in a CPSR register. Those bits change from the time to time based on the outcome of some instructions. For example, when we compare two numbers, they turn out to be equal. We trigger 0 bit. For the compare, we use the CMP mimic and followed by the operands which are to be compared. Because under the hood, the a minus b happens, which is equal to 0. If a minus b equal to 0, in this case we have equal condition. If the first number was bigger, then we have the greater than condition, and in the opposite case we have the lower than condition. There are more conditions like lower and equal, greater or equal, and so on. The CMP or compare instruction in ARM assembly is used to compare two values by performing a subtraction without storing the result. It affects the condition flags in the program status register or CPSR, which can be used for subsequent conditional execution. The following table lists the available conditional codes and their meanings and the status of the flags that are to be tested. Now let's understand this with a practical overview. I have already written the code in the CPUlator to understand the less than conditional execution. In the first instruction, I have moved the value 2 into the register R0, and in the next instruction I am comparing the value of register R0, which is 2, with the value 3. In this compare, the R2 is less than R3 and we are using the less than condition in the add operation to test out the less than conditional execution. If we go to the previous table, for the condition code less than, we require negative flag should never be equal to the overflow flag. So now let's check out the flags before we start the operation. Now both overflow flag and the negative flag are set to 0. Let's compile and run. After the move instruction, value 2 has been moved into the R0, and now we are comparing the value of R0 and the value 3. After this, you can see the negative flag has been set. For the add operation with the less than condition to execute, the negative and the overflow flag should never be equal. As you can see, the negative flag has been set, but the overflow flag has not been set. So this will execute, and the value here that was 2 will be incremented by 1. After the operation, as you can see, the value of R0 is incremented by 1. Now it is 3. Now let's take a look at the branching. The branching allows us to jump to another code or segment. This is useful when we need to skip blocks of codes or jump to a specific condition. The best examples for such cases are loops. We can also use conditional execution or conditions with branchings, like branch when the condition or the result of compare is equal, like we can use the BEQ for the branch when equal. As you can see, there are 3 types of branching conditions. Branch, it is simple jump to a function, and then we have a branch link and the branch exchange with branch link exchange. Now let's discuss stack operations. In this video, we will talk about what stack really is, how stack works, and how do we move the values into a stack, and how do we restore the values from a stack. Generally speaking, stack is a memory region within the program or a process. This part of the memory gets allocated when a process is created. We use stack for restoring or temporary data such as local variables of some function. As the stack moves from the high memory location to the low memory location. When we say this, a high memory location or a high memory address refers to the memory address that is numerically larger compared to the others within the same memory range. Memory addresses are typically represented as the hexadecimal numbers, and the higher addresses are those with the larger values. In many computer architectures, including Intel and ARM, the stack starts at the higher memory address and grows downward toward the lower memory address. When the items are popped from the stack pointer moves upward and toward the higher memory address. Now let's look at the stack operations that are pop and push. Push and pop instructions allow us to interact with the stack. The push instruction saves the register into the stack and decreases the stack pointer, and then store the specified register at the new stack location. The pop instruction retrieves the data from the stack into registers. It loads the value from the stack into the specified registers and then increases the stack pointer. As you can see in this example, where we are pushing the values of register R1, R2 and R3, they are stored into the stack simultaneously. As you can see, first the value of register 1 is pushed, then the value of register 2, and then the value of register 3. As you can see in the pop instruction, we restore the value from a stack. In this example, we are restoring the value on the top of the stack and storing it into the register R3. Now let's understand this within the CPU later. As you can see, I have already written the code where I have loaded the values into a registers and used the push instructions to load their values into the stack and pop instruction to restore those values. Let's compile and run. As you can see, the first 4 instructions loads the value into corresponding registers. As you can see, after the load instructions, R0, R1, R2 and R3 have gained the values, and after the push instruction, the values from corresponding registers will simultaneously be pushed into the stack. And now To see the pop instruction, the effect of the pop instruction, we will reset the registers. After resetting the registers, the pop instruction here will restore the values into the corresponding registers, as the first, the value at the top of the stack, that was R3, will be restored into R3. Correspondingly, the next value on the top of this stack was of the R2 will be restored back into the R2, and similarly with the R1 and R0. As you can see, after the pop instruction, we have restored the values into R1, R2, R3 and R0.